The prime counting function pi is defined so that pi of n is just the number of primes up to and including n. So that because the first prime is 2, that means that pi of 1 is 0, but pi of 2 is equal to 1. And then pi of 3 is 2, because there's 2 primes up to and including 3, namely 2 and 3. Pi of 4 is also 2, because 4 is not a prime. And then pi of 5 is 3, because there are 3 primes up to and including 5, namely 2, 3, and 5 itself, and so on. Pi of 6 is also 3, of course, because 6 is not a prime, so pi of 6 and pi of 5 will be the same. And pi of 7 is equal to 4, and on we go. Now, there's no exact formula for pi of n, but the prime number theorem, which we're going to discuss in a minute, gives some very important information. Here's a graph, just for n 1 to 100, of the function pi of n, of the prime counting function. And you can see it's constant between any two, well, it's a little bit hard to see from the scale we've drawn, but it's constant, takes a constant value between any 2 primes. So now we discuss the prime number theorem, which is the main result in this video. Pi n, the theorem states that pi n is asymptotic to n divided by log n as n gets larger and larger. And I'll give a precise definition of that down below. But the proof of the theorem is difficult and requires much more background, unfortunately, than we will have in this course. Asymptotic means that if I divide pi of n by n over log n, then that converges to 1 as n gets larger and larger. So in some sense it's saying, and we'll discuss this a little bit more in a minute, that pi of n has the same growth rate for very big N as does n over log n. And we write this, that pi n is and read it as pi n is asymptotic to n divided by log n. So the first thing to note is that it does not imply that pi n minus n over log n gets close to 0. And we give an example here. If I take n plus the square root of n, I claim that's asymptotic to n because if I divide by n, well, that's equal to 1 plus 1 over the square root of n. And as n approaches infinity, that will approach 1 because this term here is getting smaller and smaller. So n plus the square root of n is asymptotic to n. But the difference, n plus root n minus n, of course, is root n, square root of n, which approaches infinity. So what's happening, perhaps you could think of this statement here as saying that n plus root n has the same order of growth as n, in the sense that root n is very small compared with n. So the difference between this and this goes to infinity, but it goes to infinity, it's root n, but it goes to infinity much more slowly than n itself goes to infinity. So it's like a correction term, which is not as important as n. Another way of expressing this fact that pi n is asymptotic to n over log n is that pi n over n is asymptotic to 1 over log n. Now this is really just another way of saying the same thing, because pi of n divided by n over 1 over log n, well, that's just another way of writing pi n divided by n over log n, just a little bit of algebra. I've divided to go from here, which is this, to here, which is divided by this. It's just a matter of dividing in here, top and bottom, by n. So if I divide this by n, I get pi n on n. And if I divide this by n, I get 1 over log n. Expressing it this way is useful because pi n over n, well, pi n is the number of primes in this interval, 0 up to n. Think of n as being very, very large, like 10 to the 200 or something. Then pi of n over n is the average density of primes in here. So what this is saying is that for very large n, the average density of primes is like 1 over log n. Or another way of putting it is that near n, best look at it this way, roughly 1 in every log n integers is prime. Let's give an example. If I look at, say, 150 digit numbers, then roughly 1 in every log 10 to the 150, well, that's 150 log of 10, and log of 10 is 2.3, so roughly 1 in every 345 is prime. That's pretty common when you're looking at integers which have 150 digits. This is of the order of 10 squared, 10 cubed. So there are very, very many primes out there. Here's a graph of pi of x, the prime counting function. I've plotted it just for when x is an integer. And here we have the graph of x divided by log x. And remember that according to the prime number theorem, this divided by this approaches 1 as x, or really this is only defined for integers, though we could define it for any real number just by interpolating. This divided by this goes to 1 as x goes to infinity. And here's a graph of pi x divided by x over log x. And you can see it's converging down to 1, but it's actually converging down to 1 extremely slowly. Because if you look here, this is on a logarithmic scale. We have 10 to the 4th, 10 to the 8th, 10 to the 12th, 10 to the 16th, 10 to the 20, 10 to the 24. This is itself quite enormous, and yet, you know, we're only like about 1.01 instead of 1.0. And this is a starred comment. There is a better expression. If you integrate 1 over log t dt from 2 up to x, and use that instead of x over log x, then you get a much faster convergence to 1. But that's not going to be relevant to what we're doing here.